Hello, so we are back. Here we have what is it that the hidden states we have calculated about the inputs that we produced, right? So this was the input text, and we had these as the tokens, and these tokens I fed into the model as inputs, and then we got this last hidden state as the output, right? So as you can see here, there are two text. Sorry, there are two vectors for each of the text. The shape of this total hidden state is 2, 12, 768. 2 here stands for the batch size, right? 12 here stands for the number of tokens. As you can see that there are 12 tokens in for each of the text. These are 12 tokens, and this is also 12 tokens, right? You can see that in the first, like I also printed out earlier, that the attention mask of the first tensor, it has 6 1 and then 6 zeros, right? But on the second tensor, there are all ones. That means that all of the tensors are real tensors. Sorry, all of the tokens are real tokens. None of them is a padding. These zeros are called paddings. We did that padding is equal to true, right? So that is why this padding is equal to true, means that the zeros will be added there. Obviously, to fulfill the matrix multiplication requirement and the matrix shape, right? So these now what is the 768? 768 is that in which vector size each of this token is being vectorized, right? I'm saying that each of this text is being processed by the transformer, and then each of this token is stored as an information of a 768 line vector. Okay, this is the way of the transformer to store to store each token so that it can find the relationship of it with the other. Okay, so the each hidden state we have the shape of 212 Okay, now what we will do, we just saw that how to extract the last hidden state for the two text, that example text. Now what we will do, we will extract the hidden state, the last hidden state for the whole batch, or we can say the whole data set. For that, I defined a custom function that is extract hidden states of a batch. Okay, this batch will be the batch in this place of batch. We will input our data set, right? Then what we did, then we sent the input of the dictionary of the batch items. What is the batch dot items? The batch, that is our data set. It is a dictionary. As you make like, if I will do here, like, what is it? If I will code emotions encoded. This is our data set, encoded data set, convert that tokenized data set, I should say. See, it's a dictionary. This is a key, and this is the value. This is the key, this is the value, right? Similarly, this is the key, this is the value. Okay, now what we will see. So each of this key value pair is sent to the GPU, right? Because this type of calculation of the training of the model cannot be done in the CPU. Okay, it can be done, but it will be really slow. Okay, and to work with the PyTorch, the tensors needs to be in the same device. Okay, that is why I will send all of them to the available device. It may be GPU, it may be CPU, preferably GPU, right? So setting the device for all the inputs, this is done, I guess. And then we will extract the last hidden state. Again, I will turn off the gradient calculation for inferences. Then I will say last hidden state will be what? Model inputs dot last hidden state. I will extract them. I will process all the inputs. Now, what is a double star sign? This double star sign actually shows that you can process multiple inputs as one. Okay, this inputs it can be seen that what is this input? This input is itself a dictionary. Okay, this input is itself a dictionary which contains the key value pair of K and V. Okay, and what is this K and V? This K is train and V is this value. K is this validation, V is this value, K is this test, and then V is this value, right? Right. And when we have calculated this last hidden state, we have formed a variable to store this last hidden state. Then we will return this last hidden state, and firstly we will convert it to CPU, and then I will convert it into a NumPy array. I store it into GPU first. Firstly, it was stored in GPU. Now I am storing it into CPU so that it can be converted into NumPy first, right? And also we have done this last hidden state. I have only extracted in the second axis only the 0th part. Okay, why is that? Because as you can see, like if I will extract the whole last hidden state, it will extract this 212,768 whole thing, but I don't want that. I only want these variables to get extracted, right? Classic mistake. Okay. Next, okay, now what I will do, I have prepared my custom function. Okay, I prepared my custom function. Now what I will do, I will convert this emotions encoded, that was my data set of the encoded data set, that means it has been tokenized. Okay, I will set its format to torch, like it will be converted to torch tensors. And I only want input IDs, attention and mask. Okay, because like if I will see, it contains multiple, you can say, if I will show you, like I have shown you earlier also, emotions encoded train, right? It contains text, label, input IDs, attention mask. I don't want all of these. I only want input IDs, attention mask, and label, right? Because the training will be done on these things only. The model only needs these things. This text, this has already been converted into input IDs, right? So only columns I need are input IDs, attention mask, and label. Okay. So this is, I set this format to PyTorch so that it can be converted to the tensors so that I can work further with GPU. Now, emotions hidden. The hidden state for the emotions hidden will be mapped by the map function by using this function, extract hidden states. Extract hidden states will be mapped. How will the mapping be done? Train will be mapped to the train, validation will be mapped to validation, test will be mapped to test, right? So extract hidden states is not defined. It's saying, okay, so I didn't run this, apparently didn't run this cell. So now as you can see, this is being mapped. Okay, so now in the above cell emotion hidden, we have gotten the last hidden state for the training dataset of the emotions. See, now if we have gotten the last hidden state for the whole dataset, right? Now what we can do, we can actually finally do the training. Okay, see, as I have mentioned before, this is the last hidden state. We have gotten the last hidden state for the whole dataset. Now actually we can train our classifier. This whole is already trained. We are only going to train our classifier model, right? So let's train it. I guess the mapping is still going on, right? Okay, so as you can see, 16,000, 16,000, this is train, this is validation, this is test. Mapping is done. Now let's see emotions hidden, train, column names. Okay, so we have this text, label, input IDs, attention mask, and now we have this new column that is hidden state. Okay, let's go ahead. Creating a feature matrix. Now, since we have gotten the last hidden state that we have all the prerequisites to train our classifier using these features, so let's create a feature matrix. Now, what is feature matrix? We we don't need actually test dataset here. We will train the dataset. We will train the dataset of the for the classifier. We will train the classifier layer on the train, X train and Y train, and then we will see its accuracy on X valid and Y valid. Okay. Let's see what is the shape of X train dot shape and Y valid dot shape. Okay. So what is X train? I say that X train is in the emotion hidden, train and hidden state. This is the hidden state. Okay. So in this emotion hidden train dot column names, you can say that this is the training X. Sorry, this is the input for the classifier. Like I'm saying that for that classifier layer, this hidden state is going to be the input. Okay, and then this label is going to be the output, right? So that is why I'm saying in X train, in the emotion train, I took hidden state as input, and then in Y train, I took training. I took the label as the output. Okay, and in X valid, in the validation dataset, I took the hidden state as input, and why valid? In the validation dataset, the label is the output, right? I hope it makes sense. Okay. What is it? Why is it taking so much time? Okay. So we can say X train shape and X valid shape. It contains 3,000 rows. It contains 2,000 rows. Okay. And 768 columns. It is the shape of the hidden state, right? Now, what we will do, we will train this classifier on a simple logistic regression of model. You can also train it on the SGD classifier. Okay. And there is the optimizer on Adam optimizer. Okay. But for this particular video, I will just demonstrate it on taking the logistic regression, because if even I will take that SGD classifier, etc., it will probably take 5% more accuracy if you would have worked before it. Okay. So, and this is light, and keep the video short. We can just use this one. Okay. Let's see. What is in this code? What is happening? I am importing the logistic regression class from the sklearn.linear model, right? Max iteration we have taken to 3,000 so that it will converge definitely, right? Training the model, and then we are evaluating, training the model on X train, comma Y train, evaluating the model on X valid, comma Y valid, right? What this will give us? This will give us that how much our data is able to score validation on X valid and Y valid, right? In this line of code, it is actually doing the training between the X training and Y train, right? It is being trained, and on this we will see that how much it can score, right? So till then, let's move ahead and see what is this dummy classifier, right? So what is this dummy classifier? Dummy classifier stands for dummy classifier. Wait a second. Dummy classifier stands for a dumb classifier, like giving same label for all the inputs, or doing some random output labeling on all the input irrespective of the input, right? So let's say how much better it can score to a dumb classifier which doesn't know anything, which hasn't been trained, right? Which is just dumb, right? So we can say that the score is 6.634, that we can say 63.45%. Okay, so how much a dumb classifier can score? Like, okay, so which only does the guesswork. It gives the 35% accuracy. So comparing to a dumb classifier, it's still way good with a 63% accuracy. Okay, so this was how that we did the training. The model is trained, and now we can use it to get the inference. We get, if we input a sentence in it, it can give us the output for that particular sentence. Like what should be the emotion, right? This was how can we train a model with a feature extraction method. Okay, so, only you by using the training the last hidden state. Okay. Okay, so let's move ahead and see more about this output. Let's evaluate more by using confusion matrix. Now, what is the confusion matrix? Confusion matrix is like, it shows the accuracy that on which emotion it was able to produce a right output, and on which emotion it was able to produce a wrong output, and what wrong emotion it was producing by giving output. Okay, so confusion matrix, like I'm just on the first line code, I'm just importing the confusion matrix class, right? We are just creating a confusion, we are creating a custom function for the confusion matrix given the predicted y, the y which it predicted, and the actual y that it should have predicted, right? Okay, so it will create the confusion matrix on base of this data, that what are y prediction, what were true y, what were the y it produced, and what were the labels. Okay, like labels we need to give to get it more familiar, to get it an idea that what were the y true and y predict, because this value that is stored in y true is not in the front of, is like labels, right? For okay, it is like 0 1 2, but label it with the given label it can associate it with the like it will able to show us. Okay, so you can like read its code. It's not that hard. I've just used the matplotlib library, right? Okay, so let me just print this matrix. Okay, as it is visible. Okay, so maximum the matrix, like it's very good for joy, 0.8 80%. It associated joy with the correct label, and it is actually like very good, not good thing, but it's very normal thing, because in the data we had the joy matrix, joy data very unbalancedly large. Okay, and leastly the surprise, it didn't surprise, it wasn't able to associate surprise with its corresponding text. Okay, and love also. So let us see how much it corresponds to the data that we had, right? So what I will do, I will just do this. Let me just click on that. Okay, now let's just move above where we have this plots. See, I guess it's visible. Okay, so joy we had the highest data, so its probability is highest. It was able to predict it highest. Then sadness, 0.71 for sadness. Anger, then less for anger. Fear, where is fear? Fear is here, 0.56. Then love, and then surprise. Okay, so like I guess it's very visual that it actually depends on the amount of data that we trained. Okay, so if we could have gotten the balanced data, if we could have gotten the more data for anger, fear, love, and surprise, it would have performed good on these data also, right? So this was an inference that I wanted to show. Okay, so that was like how can we train a model by the feature extraction. Next, we are going to do the fine tuning. In the next video, we are going to see the fine tuning, that how we will fine tune a transformer. So what in fine tuning, what will be done in fine tuning? This whole model will be, we will retrain the whole the pre-trained model. Like these hidden states, we extracted hidden states, but these hidden states were not produced for the classification. They were produced by the model for the sake of only that, for what? The masked language processing, or we can say next sentence prediction. They were not formed for the classification task. We just change the classifier header and we just change the classifier weights, but these hidden states were not built for classification. Now what we are going to do, we are going to use the pre-trained weight. Okay, and now we are going to retrain all the pre-trained weights for the classification purpose, right? I guess you are okay. So that about those things we will talk about in next video.